This is one of those videos that I really enjoy to do. This time we will implement a well-known artificial life algorithm. This is the Boids algorithm developed by Craig Reynolds in 1986. This simple algorithm recreates the hair behavior of some animals, such as some specific species of birds, fishes, and even some mammals, such as the sheep. Boids is part of the category of swarm intelligence algorithms. In this category, it is observed that certain living beings are not particularly intelligent when they live separately. But when they live together, they can perform complicated tasks, as can be seen in ant colonies and hives. The analogy in the case of the Boids algorithm can be found, for example, in the alignment of birds in flight, in the behavior of flocks, in the behavior of a school of fish, or even in the human manifestations. The particularity of this algorithm is that the individuals or agents behave as if they were obeying the orders of a leader. But the reality is that there is no leader and each individual makes decisions autonomously. In popular culture, we can see the presence of the Boids algorithm in one of the most memorable scenes of the movie Jurassic Park. The scene shows how a group of dinosaurs of the Gallimimus species flee from the attack of a tyrannosaur running through a meadow, imitating the behavior of a flock of birds. Before starting with the implementation, I will first explain the foundations of the algorithm. From now on, we will call Boids when we refer to an individual. As I have already mentioned, the Boids do not follow the orders of any leader. That is, they make decisions autonomously based on the position of the surrounding Boids. Therefore, for each Boid, we are interested in knowing its position, the direction of its trajectory, and the neighbors around it. To recreate the movement of a Boid, we will use a direction vector, so that in each iteration of the algorithm, the new position of each Boid will be the sum of the vector that represents its position with its updated direction vector. The direction vector determines the trajectory and the speed with which the Boid moves. The trajectory of a Boid is conditioned by three rules: the cohesion rule, the alignment rule, and the separation rule. The cohesion rule implies that the Boid must always move towards the center of mass of its neighborhood. The alignment rule implies that the direction of the Boid must be the same as all other Boids in its neighborhood. The separation rule implies that the Boids must maintain a certain separation between them to avoid overcrowding. To calculate these forces, we will perform very simple linear algebra operations. Initially, we will paint the Boids across the screen using green pixels. In QBasic, we can enable different graphic modes with different color palettes. For the graphic representation of our program, we will use the graphic mode number 1, that allows us to work with a screen resolution of 320 by 200 pixels. This resolution is intended for older CGA graphics cards introduced in 1981. Using this graphic mode is purely for performance reasons. In order to observe how each void evolves over time, we will implement a main loop, where in each iteration we will calculate the forces to which each void is subjected and we will repaint them on the screen. To make the movement of the voids look as natural as possible, noise must be added to their movement. To do this, we will apply to each void a slight force with a random direction and intensity. To achieve the effect of a void in movement, it's necessary to paint a green pixel in the new position of the void on each iteration of the main loop. But you also have to erase the pixel drawn in the previous iteration. To erase the pixel, you just need to paint the pixel using the same color of the background, black in this case. Programs implemented in QBasic are usually very slow. For example, the execution of mathematical operations is very slow. However, in the initial phases of a development, we may be interested in adding a mechanism to slow down the speed of our program to reach an adequate frame rate. The speed at which a boid moves across the screen is determined by its direction vector. The angle of that vector determines which direction it travels, and its magnitude determines its speed. In each iteration of the main loop, this vector is recalculated based on the forces of attraction and repulsion that we will explain later. To make our program more realistic from an aesthetic point of view, we will modify the visual aspect of the boids. Instead of using a pixel to draw a boid, we will use a line. Actually, this line will be the graphical representation of the direction vector of the boid. The behavior of a boid depends on the behavior of the boids around it. Therefore, in order to apply the three rules of the algorithm, it's necessary for each boid to know which are its neighbors within a specific radius. The list of neighbors of a boid is obtained by calculating the Euclidean distance of the boid with the rest of the boids, discarding those boids that are outside the radius of the neighborhood. Since this computation is very slow in QBasic, we will get the neighbors inside a square area instead of a circular area. This change will not affect the behavior of the boids too much and will significantly improve the speed of the program. The cohesion force that must be applied to a boid makes the boid always go towards the center of mass of its neighborhood, thus making the closest boids always stay together. To calculate the cohesion force, it's first necessary to calculate the center of mass of the boid's neighbors. The vector obtained by subtracting the position of the center of mass from the current position of the boid indicates the new direction in which the boid should move to get close to the center of mass. the alignment force to apply to a void makes its trajectory the same as its neighbors. In this way, all the voids of the group travel in the same direction. It's important that the alignment of the void is as close as possible to its nearest neighbor and not so close to its farthest neighbor. The separation force to be applied to a void prevents them from bunching up. Therefore, when the distance of a void from any of its neighbors is less than a defined value, then it's necessary to apply a slight repulsion force on the void in the opposite direction. At this point of the development, we will make some small changes to the code to improve the performance of the application. For example, within the function where the forces of a void are calculated, we can use a single loop to calculate the forces of cohesion, alignment and separation, thus avoiding recalculating the same operation repeatedly. After applying these changes, the speed of the program should improve noticeably. Obstacles are static objects that boids must avoid. In this way, the calculation that must be done to obtain the repulsion force to avoid the collision is similar to the calculation that we do to obtain the separation forces between boids.